As a follow-up to our discussion on power from the last lesson, today we're going to talk about something that's quite closely related, but is a bit of a different thing, and that is efficiency. So I'm going to start off by comparing these two. When we talked about power, I showed you that image of the weightlifter trying to take that mass and lift it up a certain height, give it a lot of potential energy. And one of the things we said in that lesson was that anyone can do a certain amount of work if you give them enough time. But what's impressive is having a lot of power, being able to do work quickly, not just being able to do it, but being able to do it quickly. So we said power was impressive. And hopefully that image of that weightlifter I gave you kind of left you with a sense that power is kind of like strength. And in many ways, you can kind of think of power as how strong you are. Now, I often like to tell students, if power is how strong you are, then you can kind of think of efficiency as how smart you are. Lifting that weight from the ground, up to above his head was a tremendous way to show strength for that weightlifter, but it might not have been the smartest way to get that weight up to that height. There might be a more efficient way to do it. And I'll give you another example in a couple of moments and a photo to go with that. So efficiency is, I like to think of it as how smart you are, or how smart a machine is. And what I mean by smart is I mean taking available energy and applying it to achieve a certain result without losing much along the way. So to be a bit more specific, when a machine or a human does work, efficiency depends on how much energy it uses and how much useful work it does. So there's kind of this energy or this work that's coming into the machine that it takes and uses. And then as a result, the machine has this sort of output, this thing it tries to do. And if we compare the amount of energy it takes in and the amount of energy that goes out, that's sort of where we get our efficiency from. And really smart machines or smart people are able to take most of this input energy and put it towards something useful. Dumb or inefficient machines waste a lot of this energy, and they lose a lot on their way to making it useful. Here's an image that I think sort of exemplifies this really well. So here we have a guy, he's got a harness on, a tether's attached to him, it's attached around this tire, and he's trying to drag this tire on the ground. This tire is currently at rest. He's fighting against friction. He's trying to give this tire some speed. He's trying to give it some kinetic energy. And what he's doing here is a tremendous way for him to show his strength, to show power. If he's able to get this tire up to a certain speed, that is impressive. That shows that he has some power. However, if his end goal is to take this tire and give it some speed, give it some kinetic energy, this is maybe not the smartest way to do it. There's probably a much smarter or more efficient way to get this tire up to speed. And if that was the end goal here, you might say, hey, buddy, why don't you throw this on a dolly or put it in a wagon, right? Put this tire in a wagon, use those wagon's wheels to your advantage so you're not fighting against friction, and you can get that tire up to speed without having to input so much work and energy at the beginning. Maybe you take a couple skateboards, slip a skateboard under this side, slip a skateboard under this side. That would be a much more efficient way to move this tire. We could get it up to speed without expending so much energy and doing so much work. So this guy may have a lot of power, and what he's doing here is going to demonstrate that, but this is not a very efficient way to move the tire. And I'm not really ragging on him for that, because that's not really the point of this photo. The point of this photo is to show power, and he's doing that. So the equation we have for efficiency looks like this. Now, I haven't actually used a symbol for efficiency like we usually do in our equations. There are a few floating out there, but there isn't really one that's sort of used universally. So for now, this isn't an equation we're going to use a lot. I figured I'd just write the word out. So to calculate the efficiency of a person or of a machine, we need to know the work out and the work in. If we look back at the photo we were just looking at, the work out is kind of the the energy that's given to this thing, the kinetic energy this thing has at the end. And the work in is what we do to make that happen, what we do to achieve that. That's all the work that this guy is doing over here. And the same thing with power. Now, this equation looks a bit funky because it has two equal signs. And what this is showing is that there are two different ways you can calculate efficiency. You can go work divided by work, or you can go power divided by power. And it turns out whichever of these two you use, you're going to get the exact same thing. These two are equivalent to each other, and I'll just mention this briefly, because power, you might recall, is work divided by time. So to turn this equation into this equation, I would take this work divided by time. I would take this work divided by time. Because I'm dividing by time on the top and the bottom, those two divided by times could cancel out. And that's how we see that power divided by power and work divided by work really are just the same thing. Now, what you guys will do when you're problem solving is you'll kind of pick one of these or the other, depending on which one's given to you or which one's easiest to use in that particular equation. So often the biggest challenge for students who are trying to use this equation is just trying to figure out what is out and what is in a certain problem. So this in, the power in or the work in, is the total energy taken in or used. In this scenario, you could think of that as how much of this guy's energy stores in his body, the calories that he has in his body that he gained from eating his food, how much of that is he using? That's the input. And based on his facial expression and the glistening sweat on his skin, I'd say he's using a lot of calories. There's a lot of input going on here in this scenario. Now the output I refer to as kind of the energy that goes towards a goal or a purpose or an intention. So what is this guy's goal or purpose or intention? Like we said, it's to take this object and get it moving, to give it some kinetic energy. So the calories he's burning, that's the input. The kinetic energy that we're going to end up giving to this thing, that's the output. Now, typically when I give you guys a new equation, we talk about units. And this equation is kind of a funny one when it comes to units. Remember, if I want a number for efficiency, I would put in a number for work and a number for work. So if I want units for efficiency, I'll put in the units for work and the units for work. Well, the units of work are joules, and the units of work here are joules. So joules divided by joules is, well, nothing. I can cancel out the joules on the top with the joules on the bottom, and I'm left with no units. What about if we look at this part of the equation? Well, power out is going to be in watts. Power in is going to be in watts. All powers are measured in watts. Watts divided by watts is, well, they're going to cancel. I'm going to be left with no units. So efficiency has no units. It's a bit of an interesting quantity in that sense. But there is something special we do have to remember when we're writing down efficiencies. We like to express them in a certain way, and that is as a percentage. So when you write down efficiency, usually you won't just write down a number and then say, oh, I have no units and leave it at that. You'll usually write that number down as a percentage. The way I like to think of efficiency is when I'm calculating efficiency, I'm kind of asking myself a question. And that question is, how much of what we're putting in actually does something useful? And the answer to that question usually makes sense as a percent. How much of what we're putting in does something useful? 10%, maybe. How much of what we're putting in does something useful? 90%, perhaps. So 10% would be a really poor efficiency. That'd be a really bad machine. 90% would be pretty good. It's actually often tough to make machines with efficiencies, close to 100%. Let's now tackle an example problem. A student raises a 60-kilogram box 3 meters by pushing it up a ramp. The ramp makes a 15-degree angle with the horizontal, and the student pushes with a force of 500 newtons. What is the efficiency of this setup? All right, so here's my setup. I've got a ramp. It makes an angle with the horizontal of 15 degrees. The box is going to go up 3 meters. And the box right here has a mass of 60 kilograms. The only thing missing here is it says the student pushes with a force of 500 newtons. So down here, pushing on this box, I have a force of 500 newtons. So what is the efficiency of this setup? And right away, you're probably hopefully thinking, okay, so the goal, what's the goal, right? What's the output, the purpose, or the intention? And where's the input? What am I doing to make that goal happen? So the goal here is to give this box some height, to lift it up 3 meters. And what am I doing to make that happen? What's my input? I'm pushing on it with this force. So indeed, that's kind of the first thing we need to think about when we're using this efficiency equation. What's the output? What's the input? Now, I've decided here to use the work version of this equation rather than the power version. And that's because I'm sort of thinking ahead a bit here, and I know, okay, using the numbers that I'm given here, it's pretty easy for me to calculate some works, and you'll see why in a second. I'm not given any powers here, and often to calculate power, I need to find work first anyways. So I'm going to have to find the work anyways. I might as well just use it directly in this equation. And we'll do an example in the next sample there, where we use the power version of this equation. Okay, so I know I need two works. One of them is going to be an output, and one of them is going to be an input. This is the useful energy, or the energy that goes to doing something useful, goes towards my goal or purpose or intention. And this is the total energy taken in, or what I'm actually doing to make that goal happen. So right here, the goal is to give this box 3 meters of height, to raise it 3 meters, to give it some potential energy. So for my output, I'm going to be using the formula for potential energy, mgh. Now the input, what do I do to make that happen? Well, the student's coming down here, and he's pushing on the box. So he's exerting a force on it, and he's going to keep doing that until the box has moved this distance. So in this particular example, my output is a potential energy, mgh, and my input is a force applied over a distance, force times distance. Another way you can think of this mgh is using the conservation of energy formula. I won't write it down again for you here. You can look at it on your formula sheet. But that formula basically said the energy initial plus work equals the energy final. And in this scenario, we'd say, well, the box has no energy initially, and it has potential energy finally at the end. So that formula tells us that the work equals the potential energy at the end. That's kind of where we get this from. The work is the potential energy at the end. Okay, so now we're thinking we're going to plug in some numbers. So mass, I know that, that's 60. Little g, I know that, it's 9.8. The height, I know that, it's going to be 3 meters. The force the student applies, I know that it's 500. The distance the box moves, ooh. Now remember, this distance has to be the distance that is parallel to the force. So the 3 meters doesn't count. This distance is going to be this distance all the way up here, the hypotenuse of that triangle. So we're going to need to know what that is. There, that's my distance, the hypotenuse. How am I going to figure this out? Well, I have a right angle triangle here, and I know a side and an angle. So that kind of screams of using some sort of trig ratio, SOHCAHTOA. So when we're using SOHCAHTOA, just as a quick refresher, we want to pick an angle to sort of focus ourselves at. Might as well pick the one angle we know. So we're going to focus ourselves here. That means that this is my opposite side, this is my adjacent side, and this is my hypotenuse. So if I want to use this information, the opposite, to find something out about this hypotenuse, I'm going to want to pick a trig ratio that has opposite and hypotenuse in it. So that would be sine. And sine is opposite over hypotenuse. So sine of 15 is 3 over d. Then to solve for d, I need to get it out of the bottom of this fraction. So I'm going to multiply both sides by d. And then to get d by itself, I'm going to divide both sides by sine of 15. So after I do that, multiply both sides by d, divide both sides by sine of 15 degrees, I end up with this. D is 3 over sine of 15 degrees. And I can plug that into my calculator and see that d is 11.59 meters. So now I'm ready to plug in those numbers over here. Mass is 60, little g is 9.8, height is 3. The force applied is 500 newtons, and the distance that's parallel to that is 11.59 meters. When I put all that in, I get a number of 0.304. But remember, we always express our efficiencies as a percentage. So 0.304 as a percent is going to be 30.4. Quick refresher, to convert a decimal to a percent, you just take the decimal and move it 2 places to the right. Effectively, you're just multiplying it by 100. So this setup is 30.4% efficient as a means of getting this box to that height. So that means of the energy taken in by the student in pushing this crate, 30.4% of it went to actually giving that box this height, this potential energy. So that kind of begs the question, well, where did the other about 70% go? All that energy that student brought in, where did it go? Well, kind of like in this scenario over here, there's going to be a lot of friction, between this tire and the ground, between this crate and the ramp. And as you're pushing this crate up the ramp, that friction is going to cause heat. And heat is a form of energy. We'll talk about it in the next lesson. So probably that's where the bulk of this student's input energy is going. It's going into creating heat as this thing grinds across the ramp and creates friction. So 70% of what that student is doing is really just creating some heat. And 30% actually goes into lifting this thing up. So a more efficient way to do this, a smarter way to do this, might be to just grab this box and lift it straight up, where you don't have to fight friction along the way. There might be a couple other sources of energy that are where this input is going. So that 70% that we're missing might not all be from friction and heat, but it's probably where the majority of it is. Okay, let's try another example. A 500-watt motor lifts a 20-kilogram object 5 meters in 3.5 seconds. What is the efficiency of the motor? Okay, so right away, what's different about this problem is we're given a power. Right off the bat, we're told here is a power. So that means it's going to make a lot more sense to use the power version of our efficiency formula, because right away I know one of these. Now, which one do I know? Well, whenever we talk about the power of a motor, we're always talking about the power that the motor takes in, right? So this is kind of the energy, or the rate at which that motor is pulling energy out of the wall socket if it's plugged into a wall socket, or out of its battery if the motor is being powered by a battery. So when you hear about a motor being referred to as a certain number of watts, that's the watts that the motor is taking in. So this is my input power. So what's the output? What is the goal or the intention of this motor? Well, it's to lift a 20-kilogram object 5 meters in 3.5 seconds. So that whole 20 kilograms, 5 meters in 3.5 seconds, that is my goal. That is my output. So now that I've identified the input and the output, and I know I'm going to use the power version of my efficiency formula, let's go straight to it. So efficiency is power out over power in. Now, power in, we have right away, 500 watts. Watts tells me that's a power, so I can plug it in right here. Power out, I'm not given it. But I got some information here I could use to find it. And we know from our previous lesson that power is the rate at which work is done. It's work divided by time. So I'm going to replace power out with work out divided by time. And then we can figure out that work out using a similar method to what we used in the last example up here. Right? Work out, we said, what's the goal here? Oh yeah, to give this thing some potential energy, mgh. What's the goal here? Same thing, to give this thing some height, some potential energy. So that workout is going to be mgh. And the time it took us to give it that mgh, that's t here, and that's going to be my 3.5 seconds. M is the mass of the object being lifted, that's 20. Little g is 9.8, and the height it's being lifted is 5 meters. The time over which that work is being done is 3.5 seconds, and we already said that the input power for the motor is 500. So when I put that in a calculator and I crunch it all out, I get 0.56, or if I move the decimal place 2 to the right, 56%. So this is a bit of a better setup than what we had in the previous question. Here we were wasting most of our energy. Here we're using at least half of it to do something useful to achieve our goal. And again, hopefully you're wondering, what about the other 44%? Where's that energy going, right? I told you guys we can't destroy energy, law of conservation of energy. So that energy that we took in, that 44%, that must be going somewhere. Well, again, if you were to put your hand on this motor as it was running, you'd probably feel it heat up a bit. And that's kind of the really common place where energy goes to when we have inefficient systems, is we often lose energy to creating heat. Now, this motor probably is also going to make a bit of noise, right? And sound is a type of energy. So some of that 44% that's missing maybe went to creating some sound. And there could be a few other places where that energy went. But quite often, the number one place where energy goes that we don't want it to is in heat. And that's why our next lesson is going to be on heat and thermal energy.